Thank you, Professor.
All right, so let's continue from this process capability ratio, and let's define another term today. I'm going to define a term called P, which is written as 1 by Cp multiplied by 100. Okay. Now let's consider a scenario when, let's say, if Cp is greater than 1. So what we know about Cp is that, let's draw it here. This is lower control limit, this is upper control limit, this is the center line. And if Cp is greater than 1, what we know is that the specification limits are going to be outside our control limits, right? So when Cp is greater than 1, you will realize that P is less than 100. Does it make sense? So you plug in the value of Cp and you will see that the value of P is less than 100. Practically, what this means is if P is less than 100, we always have some room for making errors. This is the extra room that we have for making an error. What I mean by that is, even if my process goes slightly outside the control limits, it is still acceptable, right? It can still lie in this shaded region. So in this scenario, we have some room for error. This is beneficial for the manufacturer. They can still make a little bit of mistake. Their process can a little bit out of control, but still their products would be acceptable by the customers. Now consider another scenario, which is Cp equals to 1. P is in the subscript, okay? So let me just write this correctly. P is in the subscript. So if Cp equals to 1, this is the case when P is exactly equal to 100. And in this case, you can see that your control limits and your specification limits would overlap with each other, and you have no room for error. Okay. So people typically use this value of capital P in industrial applications to see if they have some room for error or not. So to write this down a little bit more formally, P captures the extra P cap. Let's rewrite this. P tells us how much error can be accommodated. All right. And so we always want to make sure here that Cp is greater than 1 or as large as possible. Right. Any questions on this one? Okay, so let's solve a quick example here. Let's try to find out the Cp value for process A. Can anyone quickly calculate this value and tell me what is Cp for process A? Anyone? Okay, so Cp is nothing but USL minus LSL by 6 sigma. So let's plug these values here. USL is 62 minus LSL is 38 divided by 6 times sigma, which is 2. And this is equal to 24 by 12, which is 2. So Cp for process A is equals to 2. Can you use the same formula to find out what is CP for process B?
Uh, isn't it same, Professor? Like,
Right, right, yes. So CP for process B is also, but don't you think this does not make sense? Because for process A, it is centered at 50, but process B is not centered at 50. There is a slight shift in the process mean for process B, right? So when the process mean shifts, the process capability should reduce, right? Now it is less likely to stay within the specification limits. So if the process mean shifts, we cannot use the formula of CP directly. We have to use a modified formula for CP. So if there is an off-centered process, we use something called CPK, okay? And CPK is equal to minimum of CPU, which is using the upper specification limit, comma, CPL, which is using the lower specification limit. So let's use this formula and now calculate the value of process capability. So CPK for process A will be equal to minimum of CPU. CPU is upper specification limit minus mu divided by 3 sigma. So this will be 62 minus 50 divided by 3 times 2, comma, CPL is mu, which is 50 minus lower specification limit, which is 38 divided by 3 sigma. This will give you minimum of 2, comma 2, which is 2, right? So CPK for process A is 2. Let's see what is CPK for process B. Remember, process B has a mean shift, right? So we are expecting CPK to be smaller than 2. Let's calculate and see if this makes sense. This is minimum of 62 minus the new mean is 53, right? So this is 53 divided by 3 times 2. Standard deviation is still constant, comma, 53 minus 38 divided by 3 times 2. So this will be minimum of, this is 9 by 6, comma, this is, how much is this? I think this is, whoa, 24? No, this is 15. This is 15 by 6, right? So this gives us minimum of 1.5, comma 2.5, which is equal to 1.5. Now this makes sense. We expected the process capability ratio to be less than 2, right? Because there is a shift in the process mean. So CPK in this case is 1.5. So what we conclude from this slide is that if CP equals to CPK, this means that the process is centered, okay? On the other hand, if CP is not equals to CPK, this means the process is off-centered. All right, any questions on this one? So remember, if the mean of the process shifts, you can no longer use the formula for CP. You have to use the formula for CPK, okay? Now, with this idea, let's try to solve another question, okay? Again, we have two processes here, process A and process B. Let's try to find out what are the values of CPK for process A and process B. Notice here that process B is highly off-centered, right? With a mean of 57.5. So we are expecting the CPK value for process B to be smaller than the CPK value for process A, right? So let's write this down here. CPK for process A is equal to minimum of CPU. CPU can be written as the upper specification limit, which is 65, not 70, 65 minus mean is 50 right here. So mean is 50 divided by 3 times sigma is 5 right here. So this gives us CPU comma CPL. CPL is the lower specification limit, which is, sorry, mu, which is 50 minus the lower specification limit, which is 35 divided by 3 times sigma, right? Just plugging in the numbers here. When you calculate this, you will get minimum of 1 comma 1, which is 1. Can someone calculate the value of CPK for process B? Remember, the upper specification limit and the lower specification limit are still fixed. All that is changing is the mean and the standard deviation. Can someone quickly calculate and tell me what is the value of CPK for process B?
It's still 1, Professor.
Right, so CPK for process B is again 1. Now, this would again confuse you, right? We expected CPK to be smaller, CPK for process B to be smaller than CPK for process A. Now, this is not happening because the standard deviation is also changing in this case. If you go to the previous case, the standard deviation was fixed. Only the mean was changing, right? Only the mean was changing and the standard deviation was fixed. So what I didn't tell you here is that this formula for CPK would work only if sigma remains unchanged. When sigma changes, this is where we have to use another formula that's called CPM. We have to use another formula, it's called CPM. And CPM is given as USL minus LSL divided by 6 times tau, where tau is the expected deviation from the target value, T, which is given as half of USL plus LSL. Okay, so let's reiterate this. We have covered 3 things here. Okay, first we have covered the process capability, which is the straightforward formula for CP, and it is given as USL minus LSL by 6 sigma, right? Now, if the process mean shifts while the standard deviation remains fixed, if the standard deviation is fixed and the process mean shifts, this is where we will use CPK, okay? And if both the standard deviation and the mean changes, we will use CPM as the measure of process capability ratio, okay? Now let's try to write down the formula of CPM. CPM is given as USL minus LSL divided by 6 tau, where tau is given as square root of expected value of, it's the expected deviation from the target value, right? So it's the expectation of x minus t whole square, all right? We can do some simplification here, some simple algebraic simplification, which will give us expected value of x minus mu whole square plus mu minus t whole square. Now this term, we know that this is variance, right? The first term is variance. So we can rewrite this as sigma square plus mu minus t whole square. Now, once we write this, we can rewrite the equation for CPM as USL minus LSL divided by 6 times square root of sigma square plus mu minus t square. Any questions on this one? Okay, so we can just do a little bit of simplification here. We can write this as USL minus LSL divided by 6 times sigma square root of 1 plus mu minus t by sigma whole square. And this is nothing but Cp divided by square root of 1 plus mu minus t divided by sigma whole square. Okay. All right. So can someone tell me what is the value of CPM if mu is exactly equals to t? What is the value of CPM if mu is exactly equals to t?
CP.
Right. So we'll just plug this value in and we'll see that CPM equals to CP. This is the case when the process mean is still centered. The process is still centered and CPM equals to CP. And if the process is still centered, this is also equals to CPK. Okay. So for process A, the value of CPM will be equal to CP, will be equal to CPK. And we already have this value, right? We have the value of CPK for process A, which is 1, right? So let's plug this here. For process A, this is equal to 1. Let's calculate this value for process B. For process B, mu equals to 57.5, T is equal to 50, and sigma is equal to, I think, 2.5. So we can calculate CPM as upper specification limit minus lower specification limit, which is 65 by 35 divided by square root of divided by 6 times sigma, which is 2.5 square root of 1 plus mu is 57.5, t is 50. So the difference of mu and t is 7.5 divided by sigma, which is 2.5. And then we take the square of this, right? So when you calculate this, you will get 30 by 6 times 2.5 square root of 10. And when you calculate this, you will get a value. I don't have this value. Can someone quickly calculate this and tell me what the value is? I think this should be 2 by square root of 10, which is 2 by 3.16. So definitely this will be less than 1.
It's 0.63, Professor.
Awesome. It's 0.63. So this is equal to 0.63, right? Now you see that CPM, now you can see that the process capability ratio for process B is less than the process capability ratio for process A. Do you see this? So process capability ratio for process A is 1, and process capability ratio for process B is 0.63. So there are just 3 variations. Remember this. One is the regular formula for CP. Second is when the mean shifts, but the standard deviation remains same. And the third is when both the mean and the standard deviation changes, right? So depending on what is the scenario, you can use any of these 3 formulas. Any questions on this one so far? All right, so I'll give you one more takeaway here. As I mentioned this earlier, right? In most industrial applications, in fact, in all of the industrial applications, we want our process capability ratio to be greater than 1, right? In other words, we want the value of CPM to be greater than 1, right? So to make sure CPM is greater than 1, there is a very simple condition. This was actually presented by Boyle in 1991. There's a paper called Taguchi Capability Index, and it is published in Journal of Quality Technology. And what this paper says is that in order to ensure that CPM is greater than 1, we need to make sure that USL minus LSL divided by 6 times mu minus T should be greater than 1. It's a little bit complicated to derive this formula, but this is what it actually means. Okay, and you can, from here you can write mu minus T should be less than 1 by 6 USL minus LSL. So what this expression tells you is that this is the maximum deviation in the process mean. This is the left hand side is the deviation in the process mean, right? Mu minus T. It tells that if you want CPM to be greater than 1, you need to make sure that the deviation in the process should be less than 1/6 of the width of the specification limit, right? So this is the deviation in process mean from the target. We know the formula for target, right? Target is nothing but half of USL plus LSL. So in order to make sure that CPM is greater than 1, we need to make sure that the deviation in process mean from the target is less than 1/6 of USL minus LSL. All right, any questions on this one so far? Okay, so let's switch gears and let's try to talk about some modifications into what we have studied so far. So far, what we have done is we have looked at individual components, right? We have not looked at combinations. What happens when we have a combination of components? For example, let's say you're trying to manufacture, let's say you're trying to establish connection between point A and point B. Let's say Tempe and Phoenix, somewhere in the center. And you want to have a piping connection for water supply, right? When you want to have a piping connection for water supply, you would not have just one single pipe, right? You would actually have a combination of pipes. So in order to make sure that the overall connection is of high quality, you want to ensure that each of these individual components are of good quality, right? Now, typically, if you purchase each of these individual components from a manufacturer, they will tell you what are the quality limits on each of these individual components, but they would not directly tell you what happens if you combine them together, right? So when you combine each of these individual components together, then the quality and the specification limits will change. And let's see how that changes, okay? So in many scenarios, what you have is essentially linear, not linear, let's say just combination of multiple individual components. And some cases, these combinations are linear. In some combinations, in some scenario, these combinations can be non-linear. And we'll talk about both of these two scenarios. First scenario is very straightforward and very intuitive to us, right? If you take different individual pipes, you just connect them together and that will give you a linear combination, right? And let's say if each of these individual components have dimensions of x1, x2, up to xn, the dimension of the resulting component, let's say y, will nothing but be just the sum of these individual components, right, up to xn. And in many cases, it might so happen that you are given some constants, a1, a2, a3, up to an, xn, where ai's are constant. Typically, each of these constants will be equal to 1, but there are cases when each of these individual constants are not equal to 1. Right, so for the time being, we'll just assume that each of these constants are equal to 1, and we can use the first formula, right, which is just the sum of individual components, individual measurements. So let's say here we have a linear combination of 4 components. Each of these components have dimension of x1, x2, x3, and x4. And each of these components have certain distributions. They are not fixed values, they are random values. Why random values? Because whenever you take a measurement, that measurement will always have some error. There will always be some variations, right? So that's why we say these all follow some distributions. So x1 will follow a normal distribution. Let's say x1 follows a normal distribution with mean of 2 and variance of 0.0004, right? So typically x1, the mean of x1, which is 2, is what we will consider as the nominal value. This is what is called as the nominal value, right? But there will always be some variation, some variability, which you see in terms of the standard deviation. So x1 follows a normal distribution with mean 2 and variance 0.0004. x2 follows a normal distribution with mean of, let's say, 4.5, 0.0009. x3 follows a normal distribution with mean 3, variance 0.0004, and x4 follows a normal distribution with mean of 2.5, 0.0001. And now we can write down y as x1 plus x2 plus x3 plus x4, right? Okay, so once we have y, let's ask this question. Let's try to solve this question. The question is, determine the proportion of linkages. These are linkages. Linkages. It says, determine the proportion of linkages that meet the customer specification on the overall length of 12 plus minus 0.10. 12 plus minus 10 is nothing but USL, which is 12 plus 0.10, it's 12.10, and LSL is 12 minus 0.10, which is 11.90. Okay, so we have our upper specification limit and we also have our lower specification limit. And the question is to find out how many of these linkages will fall within this specification limit, or what is the probability of this to happen. So we want to find out probability that y is less than 12.10 and it is greater than 11.90. Okay, so to find this probability, we need to first of all find out what is the mean and standard deviation of y. So let's take a bonus quiz here. Let's say the bonus quiz here is what is the mean of y and what is the variance of y.
Professor, can you slide a little bit up?
Yes, oh, sorry about that.
So the mean is 12, I guess.
Right? The mean is 12, and what is the standard deviation? Not, let's just calculate the variance. Variance is easy to calculate. Anyone else?
Variance is 1.14 into 10 raised to minus 6.
Wait, can you repeat that again?
1.14 into 10 raised to minus 6.
How did you get this?
I just did the summation of square of each standard deviation.
Oh, these are variances. These are not
Oh.
standard deviations, but I understand what you're trying to do. So when you just add them up, these are just variances, right?
Okay.
The standard way of writing normal distribution is to write down mu first and then sigma square. In most standard textbooks, this is what we write, okay? Mu comma sigma square. So yeah, you're right. We'll just add these together up. So we will get 0.0018, right? Once we have mu of y and sigma square of y, we can just write this down as probability 11.90 less than y less than 12.10 given mu of y is equal to 12 and sigma square of y is equal to 0.0018. And now we can use our standard normal distribution formula, which is phi 12.10 minus the mean, which is 12, divided by square root of standard deviation, which is square root of variance, which is 0.0018 minus phi of 12 minus 11.90 divided by, no, this is 11.90 minus 12 divided by square root of 0.0018. So you can calculate these values from the standard normal table, and when you calculate, you will get 0.982, which means 98.2% of the linkages will fall inside the specification limits. All right. Any questions on this one? Okay. So now, as I mentioned, it is not always linear combination. An individual a quantity can also be composed of non-linear combination of individual quantities. For example, a very typical example is, let's say, the resistors that you use in electrical connections. These resistors are physical quantities, right? So their resistance values will always be a random variable, right? So when you pass current through it, your voltages will also be a random variable. You know, you remember this, right? Voltage is given as I times R, right? So in this case, your final quantity, which is your voltage, is a multiplication of two random variables, current and the resistance. So given you know what are the specification limits on the resistance, and given you know the specification limits on the current, you can find out what are the specification limits on the voltage, right? This is a typical example of a nonlinear combination. So let's try to formally define what a nonlinear combination will look like. Typically, your final measurement, which is y, will be given as some nonlinear combination g, some nonlinear function g of individual measurements x1, x2, x3 up to xn. There could be a lot of examples. One example is y is equal to x1 times x2, which we just saw. You could also have y equals to x1 times x2 square plus x3 times x4. You can have a bunch of different types of combinations depending on what the application is, right? So now once we know what the nonlinear combination is, similar to the previous case, we have to find out the mean of y and the variance of y, right? So let's try to find out the mean and the variance of y. Now, typically, if it's a non-linear combination, if it's not a linear combination, it is not easy to find out the mean and the standard deviation. For instance, if I give you y is equal to x1 plus x2, if both x1 and x2 follows a normal distribution, then you can find out what the distribution of y will be. It will be just a normal distribution with the mean equals to mean of individual values, individual measurements, and similarly we can sum up the standard deviations, right? But if y is given as x1 times x2, then it is not possible to write down the expected value of y and variance of y easily. What I'm trying to say is expected value of y is not equal to expected value of x1 times expected value of x2. This is not correct. Just remember that, okay? So what we do is, let me just take this off. So whenever there is a non-linear combination, one possible way of finding out the mean and the standard deviation is to use Taylor series expansion. So Taylor series expansion for y will be equal to, the first term will just be x1, x2, x3 up to xn, evaluated at mu1, mu2 up to mu n. Second term will be again the same. The second term will be each of these individual measurements minus mu I square of and multiplied by the partial derivative of g with respect to xi evaluated at mu1, mu2 up to mu n, and then whole square of this. No, there's no square here. Summation of this from I equals to 1 to n. This is the second term, and then the third term will have the square, fourth term will have the cube, fifth term will have power 4, and so on and so forth. So after this, all of the terms are called higher order terms. Higher order terms. And these higher order terms are typically extremely small, negligible to the first two terms. So we typically tend to avoid, or we can ignore these higher order terms, and we can approximate y as just the first two terms. Okay, so this will be g of mu1, mu2 up to mu n. I have substituted the value of x1, x2 up to xn, and plus I equals to 1 to n xi minus mu I, partial derivative of d of g, partial derivative of g with respect to xi, and we evaluate this at mu1, mu2 up to mu n. Now, once you write this down, let me just extend the page here a little bit. Once we write this down, I can write down mu of y is equals to g of mu1, mu2 up to mu n, and sigma square of y. Again, this is an approximation. So to be very precise, let me give an approximation symbol here. Okay. So again, sigma square y will be equal to derivative of g, with respect to xi evaluated at mu1, mu2 up to mu n, square of this, sigma I square of this, and then the sum of this from I equals to 1 to n. So this is the formula for the mean and the variance when a nonlinear combination is given to us. This method, you can read this further. This method is typically called a delta method. Okay, I would not go too much into details of this, but I just wanted to give you the formula, the final formula for this. Right. Any questions on this one? Okay, so let's use an example to understand how we can do the calculations. Okay. The question here is, suppose that the voltage across the points A and B is required to be 100 plus minus 2 volts. Whenever it says required to be, this means that someone is specifying limits, right? So we basically have our upper specification limit as 102, the lower specification limit as 98, right? Now we assume that the component random variables I and R are normally and independently distributed with means equal to their nominal values. And we have the nominal values given here. I is equal to 25 plus minus 1, and R is equal to 4 plus minus 0.06. So USL for I is equal to 26, LSL for I is equal to 24. Right, and again USL for the resistance is equals to 4.06, and LSL for resistance is equal to 3.94. Okay, and we are also given that CP is equal to 1. So let's try to find out the voltage. Okay, we want to find out the voltage across points A and B, and we want to make sure that the voltage across points A and B is within the specification limits, right? So we will again try to find out the probability that voltage is less than 102 and it is greater than 98. Now, in order to find out this probability, again, we need to find out mu of V and sigma square of V. Right? So let's use the formula that we just have written down and see if we can calculate these parameters. Let's start with mu of V. Mu of V is nothing but the nonlinear function calculated at mu1, mu2, mu n, right? So the nonlinear function in this case is IR, and then we evaluate this function at mu of I and mu of R. So if we evaluate this, we will just get mu times mu I times mu R, right? And we know that mu I is 25, mu r is 4. So we get mu v as 100. Right. Once we have mu v, let's try to find out what is sigma square v. Again, let's go back to the formula. Sigma square is the partial derivative of this nonlinear function g evaluated at mu1, mu2, mu_n times sigma I square, right? So let's write this down. It is nothing but the partial derivative of IR with respect to I, and then evaluate this at mu I comma mu R and take the square of this, multiply by sigma square I, plus again take the derivative of this IR, this time with respect to R, and evaluate at mu I comma mu R. Take the square of this and multiply this by sigma square R, right? So now we can calculate this. Derivative of IR with respect to I is just R, and we can evaluate this at mu I comma mu R, square of this times sigma square I, plus derivative of IR with respect to R is just I. Evaluate this at mu I comma mu R, square of this times sigma square R. Now, if you evaluate R at mu I mu R, it is just mu of I, right? So this is mu of I square, sigma square I, because there's no I term here. Sorry, this is just mu square R. This is mu square R because there's no I term in the first one, right? In the second one, there's no R term. So this is just mu square I multiplied by sigma square R. Now we have the expression for sigma square V. But we don't have the values for sigma square I and sigma square R, right? We only have the upper specification limit and the lower specification limit for I and R. But there's additional piece of information that is available to us, and that information is Cp equals to 1. If Cp equals to 1 means that USL minus LSL divided by 6 sigma equals to 1. So from this formula, we can calculate sigma as USL minus LSL divided by 6, right? So let's use this formula for both current and resistance and find out the value of sigma. So sigma of, let's actually calculate here itself. Let me use a different color so you'll be able to remember this. So sigma of R will be equal to 4.06 minus 3.94 divided by 6. This is equal to 0.12 by 6, and this is equal to 0.02. Similarly, sigma of I is equal to 26 minus 24 divided by 6, which is 1 by 3. So now we have all of the values that we need. We can plug these numbers here. Let's plug these numbers. Mu of R is equal to 4. So this is 4 square, which is, let's write down this as 16 times sigma square I, which is 1 by 3 square, which is 1 by 9, plus mu of I is 25. So this is 625 multiplied by sigma square R, which is 0.02 square. So this is 0.0. This is 0.0004. So when you calculate this, I think you will get, let me see, you will get 1.99. Right, any questions on this one?
Professor, I have a question.
Um,
The CP value, which is just 1, is
that
applicable. Hello.
Your audio is a little bit blurred and it's kind of disturbed. Can you instead write down your question on the chat? I just hope it's not a cyborg. Yeah, I think Sachin, you should check your microphone. I think there's some issues with that. But definitely you can write down your question in the chat box.
I'm writing the question.
Sorry?
I'm writing the question.
Okay, yeah, go ahead. So in the meantime, let's collect the values that we have already got. So we have got two values here, right? We have got mu v and we have got sigma square v. So now, once we have these values, we can go back to the original probability expression that we have. So our original probability expression was right here. Right? We wanted to find out probability that V is less than 102 and it is greater than 98. Now we know that mu of V is equal to 100 and sigma square V is equal to 1.99. Right? Once we have these values, we just have to plug in the values. This is again a normal distribution. This is a standard normal distribution. So this is phi of 102 minus 100 divided by square root of 1.99 minus phi of 98 minus 100 divided by square root of 1.99. And when you calculate this, you will get 0.844, which means 84% of the times the voltage across points A and point B is going to be within the specification limits. Okay, good question, Sachin. So Sachin asked a question if CP value is given just for V or it is given for V, I, and R. It's given for all of them. Let me clarify this, okay? So not all of them, actually CP is given equals to 1 for I and R, because I and R, this is what is given by the manufacturer, right? So CP of I equals to 1 and CP of R equals to 1. CP for the voltage, we will have to calculate from the formula. We have to do 102 minus 98 divided by 6 times sigma. Sigma is 1.99. Square root of 1.99. All right, any other questions in this one? Yes, it's absolutely possible. Another question is it possible to have different CP values for different variables? Yes, absolutely. Because each of these different variables are essentially a component, right? You can think of that in terms of a quantity, in terms of a unit, right? So each of them are manufactured or controlled by a different process. So all of them will have different CP values. This is just a simple question. To simplify this, we have assumed that CP equals to 1. Good question. All right, so let's take a look at the last topic and then we will conclude lecture 7. The last topic is kind of very interesting. I would not talk too much into this because it's not easy to cover this in one course. This is called measurement system capability. So let's say you developed control charts and you developed specification limit. You did everything, but you know what happened? Your machine was not working properly. Let's say your machine was faulty. So if your machine was actually faulty, howsoever you control your control chart specification limit, you will keep banging your head on the wall and your process will not work. Your process will not work because your measurement system was faulty, right? So this happens in a lot of scenarios, more than you would expect. Your measurement system will always give you some error. You know, let's say you are running a process, you're manufacturing, you're doing additive manufacturing, let's say. You know, somebody will come and start jumping next to your machine, and then because of those vibrations, your part will not be correctly printed, right? So there are a ton of external factors that affect our measurement. And so we always want to make sure that when we are conducting our experiments, we are manufacturing something, we want to make sure that error from the measurement system is as low as possible, right? We want to make sure that the error from the measurement system is as low as possible. And this is called measurement system capability. Is the measurement system capable of producing stable measurements or not? Right? So this is an example here I took from my research. What you see here is that this top part is actually a poking device. You can use this device on a metal surface and you can measure the hardness. And at the bottom is a titanium alloy that I have placed, and I use this device to measure the hardness of this titanium sample. Now this device is so sensitive that even if you you know, tap your hand just like this, you would create erroneous measurements. You would induce lots of errors in the hardness measurements. So in fact, even if you try to control everything, even if you try to make sure that there are no external disturbances, you would still have some kind of error in the measurements. Whatever you try, there will always be some kind of errors. So whenever we take measurement from any measurement system, let's say Y, we always write this as X plus epsilon, where Y is your observed measurements, X is your true measurements, and epsilon is your measurement error. So whenever you calculate the total variance, which is sigma square Y, it is always equals to sigma square X plus sigma square gauge. Sigma square Y is your total variance. Sigma square X is your process variance. And sigma square gauge is your measurement variation. All right. So we always try to minimize sigma square gauge. Remember this. In fact, when it is not possible to minimize the measurement variance, then we start to use advanced methods to model the measurement error. All of the statistical methods are actually built around modeling epsilon. It's not built to model Y or X. It's always built to model epsilon. And that's another big topic that is not a part of this course. But if you go to any advanced statistical methods course or a machine learning course, they will actually start from epsilon. They always try to model epsilon because that is something you cannot get rid of. So if you cannot get rid of, you want to model that so you can understand how this behaves. Okay, so we will skip the discussion on that. We'll just try to see how we can calculate sigma square gauge. Okay, so calculation of sigma square gauge is a little tricky. Let me try to explain you how we can calculate this. Let's say we have samples 1 to, let's say, M. Okay, now if you take the same sample, let's say I take this water bottle and I measure the diameter of this water bottle using a vernier caliper, and I repeat the measurement 10 times. Okay, so I take this sample and I repeat measurement 10 times, M1, M2, up to M10. Now, typically, you would want all of these measurements, M1, M2, M3 up to M10, to be same, right? Because I'm measuring the exact same thing. But this does not always happen. Because of some errors in the vernier caliper, these measurements will always be different, will be slightly different. First time you will get 6, next time you'll get 6.1, 5.9. So this variability in measurement is coming from the measurement device, the measurement system or the measurement device, right? So by doing this kind of an experiment, now we can estimate sigma square gauge. And sigma square gauge will be equal to R bar by D2, where we all know, right? R bar is just the max of M minus the min of M. M is basically, I'm saying, from all of these measurements, right? So this is how you calculate sigma square gauge. Let's take a quick example here. It will make more sense. So the example here is an instrument is to be used as a part of a proposed statistical process control implementation. The quality improvement team involved in designing the SPC system would like to get an assessment of gauge capability, right? We want to measure the gauge capability. 20 units of a product are obtained. So we have 20 units, 1 to 20. And each of these products are measured using an instrument twice. We are taking the measurement twice, right? So the first column is the first measurement, second column is the second measurement. Now, once we do these measurements, now we can calculate sigma square gauge as R bar by D2, right? We only have 2 measurements, so we'll use n equals to 2, and we already have the value of R bar as 1, so this will be 1 by D2. I checked the value, it was 1.128, so you'll get sigma square gauge as 0.887. Now, we don't stop here. We want to compare sigma square gauge with sigma square total, right? We want to make sure that sigma square gauge is significantly smaller than sigma square total, right? Sigma square total, we will use the standard formula. The standard formula is xi minus x double bar whole square summation I equals to 1 to. We have a total of 40 measurements. We have 20 measurements here. We have 20 measurements here. So we can do 1 by 39. We use the standard formula for variance. And when you calculate this, you will get 10.05. So now you can actually compare the total variance with respect to the gauge variance. And you will notice that sigma square gauge is significantly smaller than sigma square total, right? So this is how you do gauge capability analysis. You always want to make sure that sigma square gauge is as low as possible. Because what happens is if sigma square gauge starts to increase, then you would not be able to distinguish between what is a good item or what is a bad item, right? If you add a lot of errors to each of these 2 measurements, you would not be able to distinguish between what is good and what is bad. So that's why you want to make sure that sigma square gauge is